Okay, we're working in section 10.2, and we've done a couple of hypothesis tests using the critical value method for step 4. Now we're going to look at the p-value method. So again, to remind you, we've got those formula sheets or summary pages that you can print out or reference on your screen. And so where we are is we're working on the one proportion z-tests. This is from 10.2. We've already done this, step 4 with the critical value approach. Now we're looking at this p-value approach. And so this is available to you in the summary pages, just as a reminder that kind of all these details that we go into in depth in the notes are kind of summarized here on this one page. So looking at what is the p-value. So another way of figuring out which decision we're going to make in step 4, whether we're going to reject or fail to reject the null hypothesis. Another way to do that besides the critical value approach with the picture and the test statistic is the p-value method. So instead of finding the critical values, we can find what is called the p-value. So the p-value is a probability. So we did work with probability in chapter 5. It's the probability of getting, and 6, it's the probability of getting a sample statistic or a more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true. So p-value, it's a probability, it's the area under the curve. So probability is the area under the curve, and we find it depending on the statistical test being used. So it will, again, vary if we're working with a mean where we have t-scores and t-values, or if we're working with a proportion where we have z-scores, z-values. So the p-value method, for example, using what we learned in chapter 7, we can think about this, right? What's the probability that z is less than negative 2.89, and draw a picture. So here's my 0, negative 1, 2, 3. So negative 2.89 is pretty far back there. So I've just got this little tail back there. So that's my picture. 1, 2, 3. And I can find that from the table, right? So this is a normal z. So I can look up my table 5, standard normal distribution, look up z equals negative 2.89, and find a value of 0.0019. That is my p-value, okay? So that is my area from table 5, okay? In terms of what we've been doing with our hypothesis tests and drawing our pictures, we've got the z-value of negative 2.89, and this p-value is an area, so 0.0019. So that's where we would label those two values. This probability is called a p-value. Once we have the p-value, then we're going to either reject the null hypothesis if the p-value is less than alpha, or fail to reject if the p-value is greater than alpha. And again, this little reminder is in your note packet, your summary page, right here. Once you've done your p-value, you can reject or fail to reject based on how your p-value compares to alpha. So in this case, the area in the tail must be less than alpha for us to reject h sub 0. The smaller the p-value, the stronger the evidence is against the null hypothesis. If the area in the tail is greater than or equal to alpha, then we fail to reject the null hypothesis. So here's a little picture that might help with that interpretation. This is just lifted from a textbook. So, suppose h sub 0 were true. The p-value is the probability of a test statistic value like the observed one or even more extreme. So if your h sub 0 value here is true and your test statistic is here or further out, this area represents how likely you are to get a test statistic there or further out. So it's talking about how likely it is that your h sub 0 could still be true and you could get a sample value that's kind of far out. So depending on what that probability is, you got to compare that to alpha. So if it's less than alpha, then what are you going to do? You're going to reject. If it's greater than alpha, then you're going to fail to reject. So we can also use our calculators to find the p-value. Okay, we just used table 5, but we can also use a function in our calculator. I do not think we have used this function before. I think this is the first time we're seeing this. This is still in the variables menu. So it is normal CDF, so second vars. What we've used in this menu so far is inverse norm and inverse T, and we used binomial PDF. Okay, so there's quite a few things in this menu. So now we're looking at normal CDF, normal cumulative distribution function. So we're going to enter the lower value, the upper value, 0 and 1. 0 and 1 are referring to the mean and the standard deviation. Okay, and this is the standard normal distribution, so we will always have those values of 0 and 1. For two-tailed tests, we must multiply the value from our calculator by 2, because what we're going to be finding is the area in the tail. But if it's a two-tailed test, we have area in both tails, so we need to double it or multiply by 2 to get the area in both tails. So let's just have a little example here. We just had that previous one of 2.89, right? Negative 2.89 was the example on the last page. So if we want to do this with the calculator, we need to find the lower and the upper bounds. So you always want to go left to right. So you're looking at the part that's shaded. Well, how far does this tail go? Forever. But what we can use is we can use a lower bound of negative 1,000. Okay, remember almost all the data is between 3 and negative 3. So going to negative 1,000 is quite far out, and that will be sufficient. So we can use a lower bound of 1,000, or if we had a right tail test, we'll put it in parentheses, we could use a right tail, we could have an upper bound of 1,000. Okay, we've got a left tail test, so we're saying that this purple shaded tail is going from negative 1,000 to negative 2.89. So we'll do normal CDF, negative 1,000, negative 2.89, that's the lower bound and the upper bound, and then 0 and 1 for the mean and standard deviation. So normal CDF, lower, negative 1,000, upper, negative 2.89. Don't think of lower and upper as lower has to be negative and upper has to be positive, okay? It's just the left to the right, which part is shaded, and that's what you're going to be finding. My calculator is already saying mu is 0, oops, and sigma is 1. And so then I can go from there, and here's my value. And I'm going to round p-values to 4 decimal places. I know this rounding is a little crazy. Test statistics to 2 places, critical values to 3 places, and p-values to 4 places. So 0.0019. The reason we're doing that is because that matches up with what was in table 5. Table 5 has those 4 decimal places. If you feel like you're going to lose your mind over that rounding, let me again refer you to the summary pages. It reminds you right here. Round to 2 decimal places for test statistic, 3 decimal places for critical value, and 4 decimal places for p-value. So this is a really handy guide. So that's our p-value. So let's practice. We can use the table 5, but I prefer the technology, so let's practice some technology and see what we get. So for each of these, we're going to want to draw a little picture, okay? I am going to use my lovely little stamp. It makes me happy. So suppose we found z is negative 3.14 in step 3 of our hypothesis test. Find the p-value for a left-tailed test. So there's 0, 1, 2, 3. So negative 3.14 is like way back here. So it's a tiny, tiny, tiny little tail. Okay. So I'm going to do normal CDF. And they did say it's a left tail test, so that makes sense with my picture here, right? So if it's a left tail test, I'm using the lower bound of negative 1,000, the upper bound of what my value is, 0 and 1. And I get that lovely mess, right? Scientific notation, so I've got to move my decimal point 4 places to the left. So 1, 2, 3, 8, 4, 4, 8, something like that. So if we want 4 decimal places, we'll have 0.0008. Part B, suppose we found z equals 2.45 in step 3. Find the p-value for a right tail test. Okay, so here's 0. 1, 2, there's 3, so 2.45, maybe somewhere there. And it's a right tail test. Got my tiny little right tail shaded. So now if I'm doing a right tail test, my lower bound is this z value, and my upper bound is the 1,000. So the lower and upper bound always need to go from left to right. So it's either going to be negative 1,000 up to a number, or from a number up to positive 1,000. I like to cheat in my calculator and just kind of type over the previous thing because I don't like those menus. 2.45, comma, 1,000, comma, 0, comma, 1. Remember the comma is right above the 7 key. And my value is 0.0071 when I round to 2 decimal places, or 4 decimal places, sorry. Okay, suppose we found z equals negative 1.32. There's my 0. There's negative 1, negative 2. So 1.3 is maybe somewhere around there. So my tail is a little bigger, right? So my answer should be bigger because remember, these answers are the area in the tail. So this answer should be significantly bigger than these previous 2 answers. What else is different about this one? I kind of stamped over it, but they say find the p-value for a 2-tail hypothesis test. So actually, I also have this over here, right? I actually have 2 tails. So I've got the negative 1.32, but then I'm going to kind of also think about the positive 1.32. Now, what's nice is we have symmetry, so we don't have to do it twice. We can do it like this. I can say that the area in my left tail is normal CDF from negative 1,000 to negative 1.32, comma 0, comma 1, which is 0.0934, but it's 2-tailed, so I need to double that. So both tails and I'm just going to use the rounded value since. So my p-value, my total area in both the tails, is 0.1868. Okay. So if you just have a left tail or a right tail, you can do a single normal CDF. If you've got both tails, then use that symmetry and just know that you need to double the area that the normal CDF function gives you. And what about this? Suppose we found z equals 2.63. I mean, you could practice this one and pause and come back to the video because it's very similar to part C, right? So this time the z they gave me was 2.63. Pretty small tail, looking more like parts B and A, but it is a 2-tail test. So I also have negative 2.63. So I can do either one, and then I can double it. So they gave me a positive 2.63, so I'll work out the right tail. And I get an area of 0.0043 in the right tail. So both tails, it's going to be 2 times that. So my answer will be 0.0086. And if you double it before you round it, you might get 0.0085, but that's going to be close enough. Okay. My stat lab will accept either answer. So that is what we do with our p-values. Okay, so we still have our same normal distribution drawn there, and we have some key values, but what we didn't do is draw the alphas. These were our values from our test statistic. If you notice, these z values were 2 decimal places. Those were the test statistic. And so we actually just directly draw the test statistic on there as the beginning of our tail or tails, and we find the area, and then we compare that to alpha. So again, this is a review page, okay? Hopefully it's helpful for you to kind of keep seeing the same things over and over, kind of layered on. So we have our 3 different kinds of hypothesis with our not equal, less than, or greater than, determine alpha, find our test statistic. So now we have step 4, 2 different ways, and we're going to practice doing these both ways. So what's new is our p-value method. We find the p-value using normal CDF in the calculator, but if it's 2-tailed, we've got to double it because we'll have the other tail as well. And then we need to identify the alpha level. We're going to compare the p-value and alpha, and then we make a decision based on whether the p-value is less than alpha or greater than alpha. And again, our step 5 is there is or there is not sufficient evidence to support the claim that was made in H1. So that's putting the steps 1 through 5 again back together now that we have this p-value method as well. So we're going to do a couple more examples where we are going to do both methods. We're going to do step 4 both ways. And what's nice about that, it is more work, but what's nice about that is you should get the same answer. So if you get a reject here and a fail to reject here, it's like a way of checking yourself. You know that you did something wrong and you can go back and look more closely. Okay. So your conclusion, your decision that you make in step 4C should be the same whether you did it with the critical value method or the p-value method. So here we go. Here is our question on page 17. An educator estimates that the dropout rate of seniors in high schools in Ohio was 15% 5 years ago. Last year, 38 seniors out of 200 withdrew. At alpha equals 0.05, I think it means they dropped out, not just withdrew. Is there enough evidence to suggest the dropout rate has changed? Use both the critical value and p-value methods. Okay. So what do we know? This is kind of the given. That's our p. That's what we're using as our standard. Until we can show otherwise, we're assuming 15% of seniors dropped out. Last year, 38 out of 200 withdrew. So we had a sample size of 200, and 38 fit into this certain category that they dropped out. So p hat, our sample proportion, is 38 out of 200. That's going to be 0.19. So that's high. It's 19%, right? The other information we have numerically is that alpha is 0.05. So that's kind of our pulling our information out. Then we start our 5-step process. We need to write 2 hypotheses, the null and the alternate. So the null is the status quo. They said it was 15 years ago. We're going to say, okay, sorry. They said it was 15% 5 years ago. So we're going to say, okay, it's 0.15. But what do we think? Okay. What are we looking into? We're looking into, is there enough evidence to suggest that it has changed? Did it say increased or decreased? No, it just said changed. So our alternate hypothesis is that it is no longer 15%. It's something else. And remember, for our proportions, we turn our percents into decimals. So this is my claim, and this is a two-tailed test. Because we have the difference. It could be less than 0.15 or it could be greater than. Alpha is 0.05, boring step. And step 3 is our test statistic. So let's see what we've got. Z equals p hat minus p over square root p multiplied by q divided by n. So p hat, 0.19 minus the given p null, 0.15. Oh, we didn't do q, huh? Okay, so p and q, if p is 0.15, q is 0.85. So 85% stayed in school. And n is 200. Do this all at one time in your calculator. Be sure to have parentheses around the top. Don't forget the division sign and the big square root sign. And test statistics, we round to 2 decimal places. So 1.58. All right, now I'm going to break up my page. I'm going to break up in my page into step 4 with the critical value and step 4 with the p-value. Okay, so I'm going to have a picture for each one. It is a visual picture approach. So if you're working out a hypothesis test on a quiz or a test, you do need to show all 5 steps. You need to have a picture. Okay, you need to have labels on your picture. Values along the x-axis, also some areas. Okay. So the first way that we learned, we had our critical value approach. We wrote, the first thing we drew on our picture was our tail or tails, and they were based on alpha. So here's my little note. Tails are based on alpha. So alpha was 0.05, but it was a two-tailed test. So we have 0. We have a tail on the right and a tail on the left. So because alpha was 0.05, 0.025 is the area of each tail. Okay. So then we needed to find our critical values. So we have a positive critical value and a negative critical value, and we found those with inverse norm. We are doing a lot of stuff on the calculator, so this is another reason why I want to recommend to you these summary sheets, because the summary sheets are going to remind you, what am I trying to do? How do I find it? Okay, if you're doing the critical value approach and you're trying to find the critical value, you can either use table 7 with the 0, or you can use inverse norm. When we get over into the PV, the p-value approach, we're using normal CDF. So we do a lot of different things in a lot of different cases. These summary sheets are really going to help you remind you what to do when. And while we're talking about that, the very last page of the summary packet just tells you all the calculator stuff. So it gives you a summary of the calculator directions for sample size, confidence intervals, our hypothesis test, critical values, and p-values. So this is a really good resource as well. Okay, so we've got a critical value of, what happened here? Okay, so we've got a negative 1.960 and a positive 1.960. So those are our critical values, and now we place the test statistic in our picture. So 1.58, and if this is 1.96, then 1.58 is somewhere right around there. And again, I've got to put my value down here. 1.58 is that test statistic value. Okay. My picture is kind of cluttered there, but I want to make sure I have all those details there. So, did the test statistic fall in the rejection region? No. So, we're not in the rejection region. We don't get to reject. So, our decision is that we fail to reject H sub 0. So what happens if we try the p-value approach? We just looked at it. We did something with normal CDF, but how do we make our picture? So this time, instead of the tails being based on alpha, the tails are based on the test statistic. Okay, so my picture, I'm strategically using my different colors here. My test statistic is in red. That's what I'm putting on here. Okay, I'm putting on my red test statistic of 1.58, and that is making the tail now. Now it's two tails, so I'm also putting on negative 1.58. And you don't have to have these pictures perfect, but if I've done mine semi-accurately now, what you'll see is that these red tails are larger than the purple tails. Okay? They both keep going out forever, but just the actual amount of shading is more on the red one here. So now I want to find the area because the p-value is the area. Okay? So p-value is an area. So I'm looking for the areas of these red shaded regions. Okay. Since I've got two of them, it's going to be twice the normal CDF. So I'm going to do the normal CDF for the right tail. This was my actual test statistic, 1.58, so I'm going to use the right one. So 1.58 to 1,000, 0, 1. If you want, you can type in the 2 right here too. Either way, I'm going to do the normal CDF first. So from 1.58 up to 1,000. Oh, sorry. Something's not right. Oh, I have too much in that line. Okay, 1.58 to 1,000. That's going to give me this value, and then I multiply by 2. And I get a p-value of 0.1141. So now I need to compare that to alpha. Well, alpha was only 0.05. If you want to think in percents, 11%, 5%. So this p-value is bigger than alpha, right? So 0.11 is greater than 0.05. So the p-value is greater than alpha. And then we can go to our notes. If the p-value is greater than alpha, we fail to reject H sub 0. Okay, and so this is good. We got the same conclusion for both tests. So we're going to fail to reject. There's the end of step 4, and here's my summary. So this is a bummer for me, right? I was hoping to reject H sub 0 and show that it's different, but I wasn't able to. So there is not sufficient evidence to support the claim that, okay, we can pause here. What's the claim? The claim, or what we were trying to show, is that the dropout rate has changed. So there is not sufficient evidence to support the claim that the Ohio dropout rate for seniors has changed